will respond. So please let's thank Tom for being.
Thank you. I should mention that, and you may not remember this, but I was given the name Dr. Dash by Nick.
Okay. That's why it's such a cool name. I understand.
Now, so as Nick mentioned, all of my career has been devoted to trying to understand disks, in particular the dynamics and the evolution of disks, which means that I'm limited to studying objects that exist in the universe after recombination. But that's not particularly limiting. Once you involve gravity, dissipation, and angular momentum, you've got a disk. So virtually everything in the universe has a disk, formed out of a disk, or sits in a larger disk. So, like Nick said, I've worked on all kinds of objects. I got involved with the Milky Way by a very different route. And I'm not going to talk today in detail about the dynamics, but I'm going to make some important allusions to dynamics in the context of spiral structure. But in the mid-90s at Ames, I was involved with a couple of projects involving the interstellar medium, and came to the realization that Kobe had made some observations that might actually provide some sort of insight into the spiral structure of the Milky Way. Now, naively, I thought the spiral structure, at least from a geometric perspective, was well understood at that time. So this would just be a little, adding an extra little decimal point to it. But because it involves some tracers that have not been used before, I decided to go ahead and pursue it. Well, as I turned out, the field was not nearly in the kind of nice, convenient shape that I thought it was. And so I'm going to go through the history to set the context for what happens later. So if we go back to the beginning of the 20th century, by that time we understood the Milky Way to have a disk-like structure. A lot of that was due to star counts, starting as early as the late 1700s by William Caroline Herschel, and other people in the 1800s. And then Harlow Shapley's studies of the distribution of Gaussian clusters. So by the 1920s, we understood the galaxy was probably a disk, which is accurate, but it's incomplete. And that's because of this person who mucked things up in a great way, the third Earl of Rosse, who built what was then the world's largest telescope, the Leviathan, and started looking at these nebulae and seeing spiral structure. Term of the spiral nebulae. I'd like to put this slide up from another historical perspective. The Leviathan is in Ireland, Burn Castle. It was the world's largest telescope at the time. And it's interesting when you go to a physics department and things get outmoded after 5 years or 10 years, it goes into a dustbin or something. Every telescope that has been classified as the world's largest telescope since the Leviathan is still an active functioning telescope. Now, there are no photometers mounted on the Leviathan, but it's still, it's a nice instrument. So, spiral structure, spiral nebula. But does that mean the Milky Way is a spiral nebula? Well, we didn't know. In fact, at that point, it wasn't even clear what the connection was between the Milky Way and these spiral structures. Was the spiral nebulae part of the Milky Way? Were they even, there was a broad range of things, but basically it came down to, were they island universes or local? Were they other Milky Ways? And this culminated in the great debate in 1920 between Harlow Shapley and Edward Curtis. And it was ultimately resolved very shortly thereafter with Hubble's observation of Cepheids in the Andromeda Galaxy. So, By the mid-20th century, the consensus was the Milky Way is a spiral galaxy. But there was still no proof at that time. We didn't have the observational wherewithal to demonstrate that. So, how did this get demonstrated? Well, let's understand what these spiral arms, these things that we see, these nice pretty spirals. They're what we call classical tracers of them, things that identify them. Now, with the third Earl of Rosse, basically, he was picking out the bright areas, the blue areas. And the classical tracers of the spiral arms, these are places where certain things are concentrated. Star-forming regions, OB stars, hot, bright blue stars, associations, increased gas densities, enhanced dust densities, supernovae, photo dissociation regions. So things were concentrated in these arms. In essence, they represented areas with higher concentrations of mass. And this higher concentration then led to some of these other tracers to develop. Now, inevitably, these tracers, so higher concentrations of mass. Now, this presented a problem, what I like to call the sneeze problem, because they're spiral arms, they're spiral features. How do you form them? It was known that the disk was a differentially rotating disk. If you have a differentially rotating disk of material, there are so many ways to get spiral waves. You sneeze on it, you cause little density perturbations, they get smeared out into spiral structures. Forming spiral arms is not difficult. But how to fit the various different mechanisms with how nature does it, and whether or not nature does it in one manner or many different manners presents another issue. We can talk about the broad area of why does spiral structure exist from with this grid. It's internal, something internal to the disk, or from external origin. And what about the persistence of disks? Are they quasi-stationary or are they rapidly evolving? Now, internal and long-lived or quasi-stationary, all the mechanisms produce what we call discrete spectra. And this is an area where we talk about the density wave theory and related theories. The result is we find one or two dominant modes, and these are gravitational instabilities that produce these. One or two dominant modes. It's possible that there may be tidal interactions from the exterior, but they only serve to strengthen and organize a mode that's inherent in the disk. That's one possibility. We can have external origins, and these are basically tidally driven, but they can be long-lived and quasi-stationary. We can have things that change rapidly. And rapidly changing, evolving disks, they have a continuous spectrum. So it's not just one or two modes, one arm, two arms. It's pieces and parts of many different types of arms located all over the place. And if it's internally, it can be either some regenerative process that pops up pieces of arms here and there, or it can be a recurrent thing. Come and go. Externally, it could be a one-shot tidal encounter, but it's transient. And again, it's not a global thing in nature. So we're going to come back to this after we look at the history of spiral structure in the Milky Way, and see if we can see where the Milky Way fits in this scheme, and where other spiral galaxies fit in the scheme, and whether or not they pop into a couple places. Now, we're not going to be talking about galaxies and the Milky Way that sit over here. These produce things similar to what we often refer to as flocculent galaxies. They've got all kinds of little bits and pieces, possibly coming and going. We don't know that for certain because we can't watch them over long periods of time, but they're consistent with a continuous spectrum of spiral structure. Okay, so we talked about spiral tracers, things that are concentrated in arms. And these physical objects emit radiation at specific wavelengths. And so you can do an all-sky survey at these different wavelengths that might be associated with the enhanced emissions within these arms. So here's a broad range of things ranging from the radio down to the gamma ray. And you can see in this particular, you can see that there are enhancements at certain locations. And these can represent, in many cases, but not all cases, tangents to spiral features or spiral arms. So we understand these objects exist, they're denser, these tracers exist, they are enhanced in spiral arms, and in many cases we know how to look for them. So in principle, it's a very straightforward way. We look at these emissions and we determine the spatial distribution of the sources that are yielding these emissions. Formally, it's very simple, but in practice, determining precise locations turn out to be incredibly difficult in many cases. So you know that in that direction, there is an object that's sitting in a spiral arm, almost certainly. But how far away is it? And if you only know it to within 5 or 10%, that's enough to totally disrupt your understanding of how the spiral arm structures. We will see representatives. We will see some examples of what small errors can produce in a moment. So let's go back. The goal is to understand the spiral structure of the Milky Way. What might we expect? Obviously, we're inside the Milky Way. We're inside something that's filled with dust. We're in a foggy city, dense fog, trying to map out the city. It's difficult, but we can look at other galaxies. We look at other galaxies, we can do bug collecting. We collect lots of galaxies, we try to look at the characteristics of spiral arms, if there's any commonality in shapes, of numbers of arms, of what we call pitch angles, how open or how tight the arms are. All these things we can look at other bugs, if you wish, to try to get some insight into what we might find in the home bug. The first attempts at trying to do quantitative or evaluations of spiral structure and spiral arms date from the early 20th century. But there were only a small number of galaxies for which there were good enough observations to make this assessment of what's characteristic of spiral arms. So for example, these studies had about 24 galaxies to work with. What did they find? Well, what they found was that there was, not all these systems could they fit a spiral form to. Well, they could always fit a spiral form. But they found that most of them were well fit by what's called a logarithmic spiral form. So if you take the center of the spiral, so it's at a distance r from the center of the galaxy, and you relate that to the azimuthal angle. And now this azimuthal angle doesn't just go from 0 to 2 pi, it goes up and up and up and up. That you can find a relationship that looks like this that's referred to as a logarithmic spiral. The logarithmic spiral is an interesting spiral. It is what we call a self-similar or scale-free form. So if you take the alpha here is related to the pitch angle. So it tells you how wide open or how compact, or tightly wound the spiral arms are. And A is just a scaling factor. But because it's self-similar, you could also think this is a rotation. So that changing A is equivalent to taking that form and just rotating it. We'll come back to that shortly because of some work that I was involved with. So this is the logarithmic spiral form. Now it turns out that these forms are very common in nature. They involve the way things grow. So if we, so again, this is the logarithmic spiral form. This is called the pitch angle. And it's related to the alpha by this expression. So the seeds of many different types of flowers, nautilus, pine cones, hurricanes, and, as I mentioned, some galaxies. Now, there is, in fact, mathematically, a form that's known as the golden spiral. And, oh, I should mention, this is a constant. For a logarithmic spiral, that pitch angle is a constant at all radius. It doesn't change. There is a specific pitch angle that corresponds to what we call the golden spiral. And we also see the golden spiral in various places in nature. So that's a special case. So these early studies suggested that at least external galaxies, their spiral forms were consistent with being, for the most part, logarithmic. The first large-scale study was done by Danvers at Mount Wilson Observatory in 1942, and he studied 98 galaxies. Now, even in 1942, Los Angeles was still, it was a kind of sleepy place, but Mount Wilson sits up above it. So you're looking down over the valley. And in 1942, plate materials were not real sophisticated. And so today, if you tried to do that with his plate material, the lights from the city would just, it would be hopeless to do something like this. And if you had taken modern plate material back then, normally it would have been somewhat problematic also. But note the date, 1942. Mount Wilson is a bright sky observatory today. In 1942, it would have been a moderately bright sky observatory, except it was 1942. 1942 was after Pearl Harbor, and so the West Coast had blackouts. So every night, Mount Wilson became a dark sky observatory. So what did Danvers find? Well, he found that logarithmic spirals provided best fit to most of the galaxies he looked at. Now this came into question 4 decades later. Particularly Kinematic argued that his plate material was so poor that he didn't say it negated his result, Danvers' results, but it rendered them questionable. So a lot of follow-up studies were done, and I just listed a tiny number of them, and they basically support Danvers' conclusions. That is, most external galaxies have logarithmic spiral forms, but there distinctly are exceptions. And it's worth noting, and I'm not going to talk in detail about spiral density wave theory, but that theory fits in that first box we looked at on our grid of possible explanations for the nature of spirals. Spiral density wave theory predicts logarithmic spirals. So that's a form. What about numbers of arms? Can we get any guidance from external galaxies also? I should also mention, although the external galaxies suggested logarithmic forms to be a very strong possibility, it says nothing about pitch angles. So we didn't get any insight into pitch angles for galaxies by looking at external galaxies. We look at the numbers of arms, external galaxies. We see one-arm galaxies. We see two-arm galaxies. We see three-arm galaxies. We see four-arm galaxies. We see five-arm galaxies. And we see galaxies where the arms are so tightly compacted that it's kind of hopeless to even imagine or count. Though at that point, you start to wonder if there are that many discrete modes. I've done a lot of work, and a lot of people have done a lot of work at looking at modal structure in disks that are subject to cooling. Now, many disks hover around marginal instability to gravitational instabilities. What happens is, in a gaseous disk, you are losing energy by radiation. So that cools a disk. At the same time, you're heating up a disk by collisions and shocks. That heats the disk. And if you look at these analyses of how susceptible a disk is to gravitational instability, you can use as a proxy the Tumorite Q factor. And the linear analysis says, which there's analytic expressions for. But the point is, many disks are thermostatic. So they will cool off to the point where they form these instabilities, these structures. Those structures then cause heating of the disk, which heat the disk, which lower the instability. But they will hover around these instability levels. And if you look at huge numbers of disks, gravitationally unstable disks in a variety of contexts, you find that there are the eigenmodes that give these the spectra of these instabilities. And depending upon the object, you see that m equals 1 or 2 or 3 or 4, even up to 6 can be important modes. But typically, the dominant modes are m equals 1, m equals 2, m equals 3, m equals 4. So anyway, we don't get a great deal of insight from external galaxies, except that it's consistent with these low order modes being the dominant source of these arms. So external galaxies, they don't provide us a lot of guidance in our search for spiral structure in the Milky Way. So as of 1950, we still didn't have any concrete evidence that the Milky Way was a spiral. But that changed starting in 1952. So in 1952 and in 1953, there were observations of bright blue giants, blue supergiants, in the galactic neighborhood. And so here's the sun right here, and these are basically little segments of spiral arms, but they line up very nicely in a manner that was strongly suggestive of spiral structure. It's just that we could only see the local pieces of it. Later in the so these spiral structures in the local neighborhood, these were done at optical wavelengths, but they were limited to nearby structures. Later in the 1950s, when radio technology was starting to advance, surveys of the sky, so this is galactic longitude here, so basically scanning along the galactic equator, what Mills found were these little bumps, we call them stair steps. And Mills argued, well, what's being seen there are tangent directions to spiral arms. He hadn't demonstrated this, but it was another piece of evidence that spiral structure really was present in the Milky Way. So throughout the 1960s, we could do nearby structures using these optical means. More distant and global, we could use 21 centimeter, and those promised a lot of hope for being able to decode and decipher the galactic structure. Progress was sort of being made, but it was slow. Then there was a big conference in 1970, University of Maryland, the Spiral Workshop, to look at the state of affairs. And their point was, at present, the only method of studying the large-scale spiral structure of the entire galaxy remains observation of the 21-centimeter line of neutral hydrogen. So that, in essence, was the only game in play. So 1970, only 21 centimeters were available. There were suggestions that we saw tangent directions to spiral arms. There were optical pieces of spiral arms, but they were only local. Unfortunately, when you tried to tie together the 21 centimeter and the optical, they didn't agree with each other. And at this time, there were only 2 global models that have been proposed. And they were based on the same data, Kerr and Kerr and Weaver. So these were taken from their paper, but basically they are the same radio data. And Kerr and Kerr said, oh, there's 4 arms. Weaver et al. Said 2 arms. We will see what part of the problem is in getting from here to here in just a moment. But the only agreements of the 2 models as of 1970 was there's global structure and spiral arms. So we're not a flocculent galaxy. And there was general agreement there was an arm tangent at 50 degrees galactic longitude to what we now refer to as the Sagittarius arm. There is a strong feature that we sometimes call the local arm or the Orion arm. It was agreed that this had nothing to do with global structure, spiral structure. There are many different observational indications of this. We will see manifestation of the local arm later, because it really is a very prominent feature in the sky. But it doesn't fit into the global spiral structure of the Milky Way. Needed new ways of tackling the problem, and these came online fairly quickly. And most of them fall into one of these broad categories: spectrophotometric distances, kinematic distances, velocity field mapping, tangent point fitting, emissivity mapping, D-field, electron. All of these have underlying assumptions which introduce possible errors. So spectrophotometric, this is good for local, and these are the most accurate. But because they're limited to local spiral structures, we can't decipher the global. And there are sources of error in these determinations of distances. They've been beaten down over time, but there's still some problems. Kinematic distances. These are distances that are derived by assuming a kinematic model for the galaxy, which is in essence what the rotation curve of the galaxy looks like. Coupled with that, in many cases, you need to make assumptions about velocity dispersions at various locations. And they've been used for lots of different estimates and determinations of spiral structure. These are not unique interior to the solar circle for the simple reason that if you have a line of sight interior to the solar circle, there are 2 places where the rotation curve will give you the same radial velocity. There are ways to differentiate between those 2 locations in most observations, but not in all. And there are many sources of error, and these typically, when you add them together, give you uncertainties in distances of 10 to 20%, which are really game killers for accurate determinations of spiral structure. This is an example of, again, a specific set of data, so velocity data for a set of H2 regions, filtered through 2 different kinematic models for the galaxy. And George Lynn, with their kinematic model, ended up with 4-arm model. Dash, with his kinematic model, the one he used, ended up with 2 arms. Point is, same data, different assumptions. There was a lot of hope when these velocity versus longitude maps came online. So for a given longitude, you look at the radial velocities and intensities, and you would get maps that look like this. And it was realized what you're seeing here is really a manifestation of the structures within the Milky Way. But you're still, you don't have that third dimension, so you have to extract that. How do you extract it? You need a kinematic model. And then you play around with the model and density. You also need densities. So you make assumptions about densities in a kinematic model, and you end up with a model. You fiddle with it till you get what you consider a good fit, and then voila, you've mapped the spiral structure. There are problems with this, but this was thought to be the real game changer when this was introduced. People don't do this anymore because it was realized that it wasn't producing consistent results. Tangent point fitting, and this is where we talked about this early thing from Mills. So you would see tangents on both sides of the center of the galaxy, and you would try to match that up with one on the other side and say this is the same spiral arm going through, and derive from that with some underlying assumption about the spiral form, because usually you only have 2. You don't have that third tangent point. And so with only 2 places, you're not constrained that strongly on the spiral form that you use. And also there may be an issue with tracers that they're lacking at or near the tangent point. Emissivity mapping. This is related to the tangent fitting with a third, with an added piece of information. So emissivity models, you make an assumption about the spiral structure, the emissivity of a spiral arm. And you could involve that with some sort of beam that you're observing, and you end up with structures where you say, oh, here's a tangent, here's a tangent. Actually, it turns out not to be precisely those tangent points. It depends upon your beam size and the beam details and how the emissivity falls off the distance. But this is reminiscent of the tangent point fitting, except that now you've got information at other distances. So the fact that you don't have that third point to fit the structure becomes much less important. And we'll be coming back to this. A couple of others that were used and tried but really didn't produce anything that was particularly long-lasting was trying to map the B field of the galaxy and the electron density maps. The electron density maps actually weren't totally independent of earlier ones. They basically were used to extend earlier arm models. So there's this variety of different approaches, and they yielded results. So what did they tell us? Well, there were 100 models that have been published since those 2 models in 1970. Of these, approximately 60 of them are grand design models. Of those, 68% of them have 4 spiral arms. 17% have 2 spiral arms. 5% are a superposition of 2 and 4 arms. Basically, if you think of the modal, if you have these gravitational modes, you can have more than one mode excited. So about 5 are consistent with these multiple modes. 10% is only what you might call complex. And of these global models, half of them are logarithmic spirals. How well did they agree? Well, on pitch angles. Pitch angles range from 5 degrees to 31 degrees. Not exactly good agreement. And this is just sort of an overview of a set of these models. And if you look at them for a little bit, and I'll come back to this, but this is a model that I was involved with Wolfire and Hollenbach. And I only put it in background here so that you'd have something to intercompare these different models with. And these range, these go from 1970 through to 2015. And if you look at them very long, you start to see that they're all over the place. And what's more, if you look at them systematically through time, there's some convergence, but it's not an enormous amount of convergence. So, let's come up to the last 5 years and say, okay, what's going on? What's the state of affairs? Can we get an insight into these wildly divergent models? So I'm going to call this a tale of 2+ models. And I'm going to start with Churchwell et al. In 2009. They did a tangent fitting approach using data from the Spitzer Space Telescope. In particular, the Galactic Legacy Infrared Midplane Survey Extraordinaire, GLIMPS. I apologize, but for the later model I'm going to talk about, we didn't have time to come up with a clever acronym, but that seems to be a very important part of any modern scientific study. So, the GLIMPS survey, it was snapshots of, well, a little over 100,000 positions on the skies and images in the near infrared. And basically, so this is a view of the GLIMPS catalog. They did star counts. Remember when we first went back to late 1700s to try and understand the structure of the Milky Way? Star counts. Well, now we're coming back to star counts. And this is what their study did. So they bin things in 1 degree squares to within 1 degree of the plane. And this is a really complicated looking figure. But let me just summarize. Basically, the red and the blue correspond to longitudes on 2 different sides of the galaxy. The ranges for some of the classic arms are put, so Centaurus, Norma, 3 kiloparsec arm, down here in the red, Sagittarius, Scutum. And in some places, you notice, so like the normal arm, you don't see any bumps. You don't see any enhanced numbers. But if you look at the Scutum arm, you do see this nice big bump. So it's suggestive that they're seeing some spiral arms, some tangents of some arms, but not others. So what came out of their study was they decided that the galaxy was essentially a 2-arm system. I'm sure you've seen this picture. This was something that NASA put together to go with their study. And it actually does show all 4 arms, but they didn't see 4 arms in the GLIMPS study. But the NASA artist put it in anyway. So, and these arms, the 2 arms, originate at the end of a central bar. This is not just any bar. This is a huge bar. There's still a lot of speculation, debate about the size, the strength of the central bar in the Milky Way. This is by far the largest suggestion of a bar that's in the literature. So it's 4.4 kiloparsecs extends from the center of the galaxy. 2 of these arms, the 2 arms they saw, are classically identified arms. 2 of them they didn't see. So their decision, or their argument is, it's a 2-arm spiral. There might be the other two arms in there. We don't see them, but there are two big arms. And these are in the older evolved red stars. So that's what they're seeing. They're seeing red giants and supergiants. Now I said it was a tale of two models. So then let's go to my model with Wolfire and Hollenbach. We use the emissivity approach. And we use traces that hadn't been used before. This carbon plus and C plus, carbon plus and nitrogen plus. These actually are incredibly potent tracers of the spiral arms, but you can't see them from the Earth's surface. You have to get out into space to see them. And until COBE came along, there was no all-sky map available. And since COBE came along, we've still got the COBE map. That's it. That's the only game for mapping. So both these lines are very strong coolants of the interstellar medium. Carbon plus is the dominant cooling in a couple of the faces of the interstellar medium and PDRs. Both of them are very sensitive to temperature, density, and incident far UV and UV flux. All of these are highly concentrated in the spiral arms. And there's an added advantage. These can effectively be treated as optically thin emissions. We won't go into the arguments now. But that means we can see these emissions over all the galaxy. A lot of tracers you can't see except over a limited range of the galaxy. But unfortunately must be observed from space, which means, in this case, COBE. A secondary mission, and this was thought about in the planning of COBE, was realized that the spectrum range over which they were looking at the microwave background included many important cooling lines of the interstellar medium. And so the data products included the intensities in these lines. These are what we used. And so we went through and we pulled out what does it look like if you scan along the equatorial plane of the galaxy in these lines. So this is the carbon plus, this is nitrogen plus, here's the galactic center. As you can see, they look very, very similar. But carbon plus is about an order of magnitude stronger than N plus. And you can see these strong peaks. And this is what leapt out at me when I started doing this is, well, those must be tangents to spiral arms, which led me down this multi-decade examination. I mentioned the local arm, and I told you it's strong. This is the local arm right here. We're looking right down the local arm, the Orion Arm. But again, it's local. So it's not part of what's going on here. It's a spur. So what did we do? First, we spent a lot of time thinking about how do you come up with a parameterized expression for the volume emissivity for one of these coolants. And we derived one, and it turned out there are some ancillary data of looking at carbon plus in small regions of the galaxy and in M31. And that gave us some clues as to at least the functional form of how C plus and N plus might fall off away from line center. Then we generated 100 million models for individual lines. Each of those lines had a different geometry in terms of pitch angle, but remember you can rotate. If you change that you're really just rotating that figure. And the functional dependence on that comes out of the parameterized. And then we took these models, we convolved them with the COBE, the FIRAS beam, and so this particular spiral arm would give us an intensity profile that looked like this. Now, remember, they're optically thin. That means we can do just add together arms and see what we get for the full distribution of arms. So we used a least square approach to find the best 2-arm, 3-arm, and 4-arm combinations to fit the observations. And this is the result. So the red, as we've seen before, that's carbon plus, blue, nitrogen plus, and the model predictions, which you can see here, the dashed lines. Again, the local arm isn't part of the global feature, so it doesn't get modeled. And we can break it down, and we can see the contributions from the Sagittarius Carina arms, Gudum Crux, Norma Cygnus, and the Perseus arms. We see all 4 of the classic arms, and we can understand their strengths. Now, there was one fascinating thing that came out of this. And so we get all the information about these 4 arms. And they have, and only the logarithmic spiral form, we looked at other spiral forms, only the logarithmic form gave a good fit. There were no 2-arm models that would fit the Kobe data. But there's a well-defined 4-arm model that provides an excellent fit. The pitch angles are slightly different for the 4 arms, but not largely different. And these 2 arms begin and end at a central bar. That central bar, 3 kiloparsecs, not 4.4 kiloparsecs. And this is an interesting distance, because this is where the old, it used to be called the molecular ring, and from a dynamical perspective, it's where many people think the inner Lindblad resonance is, so you don't necessarily expect the arms to continue inside that. But one fascinating thing was, remember we did a least squares fit, linear fit, which means there is a multiplicative factor for each of the arms. And that multiplicative factor basically scales the emissivity. And we didn't find a big jumble. We found 2 numbers for emissivity. One for 2 of the arms, and the other for the other 2 arms. And they differ by almost exactly a factor of 2. So it's almost as if there's 2 different sets of arms. One with one scaling for basically what might argue star formation rate, if you wish, and one for another. And this is what, seeing the model. So here's the sun, here's the central bar. So let me go back to these 2 different models I just mentioned. There's no 2-arm model that fits the Kobe data. There's no signature of 4 arms in the glimpse data. These are both very good data sets. So what's going on? Is there any way to reconcile these? Well, it turns out that there is. And to do this, let's go back and real quickly re-examine the historical record. So I've gone through every model that's ever been proposed and extracted all this information. For 4-arm models, this is the basis on which the determinations were made. It's a big, broad range. 2-arm models, there aren't quite as many, and these are the basis on which the determination of the arm structure were made. But when you look at those more carefully, what you find is the 44 that have 4 arms, they're overwhelmingly based on tracers associated with star formation and gas and young stellar populations. In fact, only 2 of the 4-arm models are based upon evolved stars, giants, supergiant red stars. And of one of those 2, the authors said they could rule out an equally good 2-arm fit. So that's what's just defining these models. What about the 2-arm models? 5 of these 10 are based upon observations of K&M giants and supergiants. And all but 2 of these, since 1985, are based upon this set of objects. So we have 4 arms, we've got 2 arms, but very different sets of tracers. Young populations, they predict 4 spiral arms. Older evolved stars predict 2 spiral arms. Okay, so where do we go from here? Well, let's pose a what if. What if the old evolved stars have a different spatial distribution than the gas-rich spiral arms? And what if the 2 stellar arms, the Kobe-Cs, represent the true spatial distribution of the density perturbations in the galactic disk? So we've got a disk, but we've now perturbed the density field with these spiral arms of Kobe lines. I'm sorry, that are seen in the glimpse survey. Well, there have been studies, what happens if you put in a 2-arm spiral potential and then you toss gas into it? What happens? Well, for certain portions of parameter space, unfortunately these are all 2-dimensional models, but nonetheless, for certain parts of parameter space, the gas settles into 4 spiral arms. So, 2 stellar arms and the gas goes into 4 spiral arms. Now, I have to mention that none of these spiral arms, gas arms, match the stellar arms. But this is young stuff. This could be an issue dealing with, there are lots of ways that this might not be an issue. But, so let's assume for a moment, well, okay, what if this is true? Are there any external galaxies that might give us suggestions that this might happen? Well, actually there are. This is MGC 309. This is in the visible. If you count the arms, there's 4 of them. This is in the near infrared. There's 2 arms. So this would be an external galaxy that's consistent with our what-if model. So we can say that the 4 gas-rich arms of this Milky Way may or might be a response to the 2-arm density perturbations. And there have been some suggestions over the years that maybe this is what's happening. There's a bunch of cautionary notes dealing with the glimpse model. I don't want to get into it, but there are some issues that need to be resolved to get great confidence. I mean, some of these, bumps are not very big. And they basically assume, and there are reasonably that in some cases there may be some serious extinction. But I say some reason, it has to do with reddening. But I'm not going to say that they got it wrong. I'm just saying that there is reason to, as is true, I mean, I'm sure we can find some issues with our model too. I mean, for example, the beam size for Kobe is far larger than we would like it to have been. So, but nonetheless, but what if we compare the two? What if we compare their model with our model? Now these are scaled to the same size. If I overlay one on top of the other, the dark lines is their model. The dashed line they didn't see, but that's those are those lines, those are those arms that the NASA artists stuck into their model. But consider this line and this line, those are the arms that the glimpse people saw. And the underlying gray is our model. Now remember, their arm is from here to here, ours is from here to here. But pretty close to the same angle relative to the line of sight. The reason why I want to show this is, remember I said we find suggestions that our gas or star-forming arms are slightly different. They're two different sets. The ones that correspond with the stellar arms are the ones with the higher emissivity, and therefore arguably higher star-forming rates. Again, by a factor of 2. These are observations. These are not arguments about what's going on. So, let me just summarize. So, Milky Way unambiguously has 4 arms in the young component. In the older stellar component, evolved component, there's arguably only 2 major arms. The bars, well, the COBE data is totally inconsistent. I should rephrase that. The glimpse bar is totally inconsistent with the COBE data. They don't see the bar. They see it in terms of where arms are and in terms of, well, they actually do see the bar. But there is a little gap which they don't think is real. They assume that it's being filled in, and therefore they think their bar is bigger. But I want to leave you with this consideration. We've talked about the history of Milky Way and external galaxies, and we see that, I think unambiguously, Milky Way has 4 star-forming spiral arms. Remember we talked about external galaxies, and we see all different numbers of spiral arms. But 2 is by far the most common. Does that mean the Milky Way is not common? And if it's not common, is it possible that 2 of the arms are transient arms? Because 2 of the 4 arms are sitting in what arguably may be the modal structure produced by that resulted in the stellar arm distribution. It's a question. I don't know the answer to it. On the other hand, it could be the reason we don't see a lot of 4-arm spirals is we do know that a lot of 2-arm spirals, they have beautiful grand designs. M51 is an example, M81. We know that those are tidally driven. So they are not showing us information, well, they're not giving us information. They're different beasts, in a sense. And we know that there's lots of tidal interaction possibilities in the universe. So it could be that the Milky Way has 4 arms and not 2 because it hasn't had, at least recently, one of these tidal encounters. I find it intriguing that there's 2 sets of star-forming arms, and that the ratio between them seems to be really, really close to a factor of 2. It could well be a coincidence, but it's an intriguing number. Finally, we may actually be getting down to the point where we're starting to narrow in on the spatial distribution of the arms. Remember, there are all those studies that try to extract arm geometry from motions, but they needed a kinematic model, or rotation curve. If we assume we know the geometry, and we know what these velocity versus longitude maps look like, in principle, you could invert the problem and get the kinematics that's consistent with those maps. And finally, more physics will always produce something. One of the problems with lots of gas dynamical models, the studies of the disk dynamics, it's always a resolution issue because these models take a long time to run. They're computationally very expensive. It may be that with higher resolution and with a 3rd dimension, some of these results in terms of how gas flows into these 4 arms in a 2-arm potential might change. I don't know. So anyway, that's for your consideration.
A
Few questions?
Okay.
Two questions actually. So let me, one leads into the other. Let's see if I get the timeline right. So let's say that the Milky Way started with a 2-arm structure, roughly, right? At which point you get an older population, an old stellar population. At some point in the Milky Way's history, there's a influx of gas, which then creates a perturbation, which then generates a 4-arm structure. Is that?
The models don't say anything about the history.
Okay.
In terms of modal structures, if they are true eigenmodes, they don't care about the past. They adjust to whatever the conditions are.
Okay.
So they don't give you any clues to history. In terms of the gas, the models had to put gas into this configuration somehow. That's always the real bane of numerical modeling. You have to select initial conditions. And how do you do that? Well, don't assume that the initial conditions for a numerical model bear any relationship to the history of the system.
Okay.
So it's tantalizing, it's interesting, but it doesn't give us any insight into the history.
And I guess the second question then is that if, so it's, you were talking about how you used emissivity and a sort of chemical, almost a chemical analysis to determine the 4-arm structure. Could you do a similar analysis, say on the hypothetical 2-arm structure? I mean, you said that your emissivity doesn't generate a 2-arm structure, but say if you just did it, say on what would theoretically be that 2-arm structure.
There's a signal to noise issue.
Signal to noise.
That's in the stellar. The only place you see the signal of where you've got enough of these evolved stars along the line of sight is congregated in the tangents. They're clearly going to be all along the spirals, but they're not enough that they show up. Whereas C plus and N plus are very powerful emissions. And so that's why you see the range of them.
I see. So
But there's no other tracer equivalent to C plus and N plus that we could do the same exercise with.
Okay.
Maybe one more question? Okay.
So you said there's 4 gas arm and 2 stellar arm, right? Does those 2 of the gas arm overlap with those 2 stellar arm geometry?
Yes, and that does. So the solid line are the glimpse arms. They're the stellar.
Yeah.
And you see the underlying shaded gray.
Sure.
So the shaded gray are our 4 arms. So if you notice this, there's good correspondence between, it's not perfect, but there's good correspondence between them. So yes, I mean, they lie on top of each other.
Okay, then my next question on that is, do you see any difference between those 2 gas arms that has a stellar component versus those 2 gas arms has no component? Do you see any difference in the actual code data in terms of the gas?
But the only difference is the scaling emissivity for this one and this one is twice what it is for these 2. So they are stronger arms.
Yeah. Is that anything related to the reason why one has stellar component and one has physical?
At this point, it's just an observation of what fit is. There's no reason at this point to have there's no underlying physical motivation to expect that. Whether it's irrelevant or not, you don't know.
I could leave with just like a closing comment. A lot of people here study dwarf galaxies, and there's been a tremendous increase in their interest because of cosmology and data. But the problem with dwarf galaxies has been around for a long time, and finally people are getting tremendous insight into this. This problem's been around even longer, and people have just kind of, for the most part, forgotten why galaxies have spirals, because no one has clearly figured it out. It is a huge problem that's still sitting out there for someone, and this looks like a really interesting discovery here, to solve this problem. Why do galaxies have spiral arms? And it's still not understood, and yet they're ubiquitous in the universe. And the problem's been around so long that people just kind of like forget about it these days. And it's really cool that someone's still thinking about this, because I hope this gets solved in my lifetime. Let's thank the speaker again.